1, we're going to be doing section 2.8 today. Get kind of hit list to mostly remind me not to miss stuff. Major part of today is going to continue where we kind of touched on at the end of yesterday. We're going to look at how do you make a simple sketch of the derivative function when all you're given is a sketch of the original function f of x. And we did curves, and that's where I'm going to start, but we're going to look at polynomials, right? Like up and down curves. We're going to look at ones that are straight lines, almost straight lines and corners to them. They're going to be a little bit different. We're going to look at vertical asymptotes, right? So what does a derivative function look like when the original has vertical asymptotes on it? And the fourth one is we're going to look at functions whose derivatives have vertical tangent lines, but the original function do not. So that's non-vertical asymptotes mean. And then once that's finished, we're doing something totally different. It's not really connected to this, although it's connected to derivatives. We're going to look at the idea of finding what are sometimes called multiple derivatives. We know how to find f dashed of x, and then we're going to look at the second, then the third, and then so on. There's no limit to what you can do. And lastly, we're going to add to our shortcut list. Now, right now, the shortcut list that we've got only does polynomials, right? It only does 5x cubed minus 4x squared kind of things. We're going to add to this radicals. So how you find derivatives of square roots of things and cube roots of things. So that's, well, thank you. He's in with squeaky. Right, well, let's start with the first kind. Stop doing that, you little bugger. Let's do polynomials. What I'm calling curves. The homework question of these basically gives you a function, the original, and then there's an A, B, a C, and a D, and you have to pick the right one. So let's imagine the original function is this guy, the f of x. So let's do an up, a down, an up, and a down. Right, there's a pretty standard looking polynomial function, one with curves in it. Now, when it's polynomials, the kind of strategy that you do, the first thing you do is you look for tops of hills and bottoms of valleys. In this case, those 3 points there. Because what I know for sure is that these are all horizontal. And horizontal means the derivative will be 0, right? The slope of a horizontal line is 0, right? So a horizontal tangent line will generate a 0 derivative. Now, that guy there, drop him down with a kind of invisible. These dotted lines, by the way, are just invisible. They're not really there, but they help me get positioning. And they also kind of help to see the thing being separated. So they're like, what would you call them? They're like construction lines that you would use in tech drawing, where they're there to help you construct the thing, but they're not physically there. Are you happy about those 3 dots and how I've got them? Why I know that at these 3 places, the curve has a 0 derivative. So here is the original. And when we're finished, we're going to have a sketch of the derivative. Now, when you put in these 0 derivatives, what you're going to do is you're going to split the shape into regions. I'm calling them 1, 2, 3, and 4. And what you do now is for each one of these 4 regions, you look at the curve. And normally when you do a polynomial, every single point in that curve will all have the same direction to its slope. Would you agree that all the tangents on this piece of the curve Aren't they all sloping upwards and so positive numbers? So I know in region 1, the derivative is positive, and positive then is positive y's, right, going above the axis. So you shade it in. In region 2, would you agree that if I chose any of these points, wouldn't the tangent line be pointing downwards? So in region 2, we're talking about negatives. In region 3, it's back to being positive. And region 4, it's back being negative. Now, against these shaded things are not there, they're just helping with the construction. The only thing that's truly there is going to be these 3 dots and the curve that I'm now about to do. Because what this tells me is that the derivative curve starts in this region, reaches that point where it crosses the x-axis, stays in this region for a little while, then comes back to here, then it goes to here, then it goes back to there. And what you do is you do the simplest, smoothest curve that does that. And we have now done our polynomial. Now, the only piece of that entire bottom that's really there is this guy. Let's see all these dotted lines and shadings. They were only there to help me get the answer. If they distract you, you could just do them in pencil and rub them out when you're finished, or just do them very faint so that you don't really see them unless you look hard. Me, I don't mind that I can see them, because what I'm looking at is really the curve. I don't see anything else of interest. Any questions? Or are we good? Can't see anything? Good to move on? Okay. So, check, done. Second thing we're going to do are functions that are made up of straight lines. Now, it's not going to be one straight line because that would be far too easy. We're going to do functions that are made up of a number of straight lines. So this is the original function. So it's going to go up the way to here, straight to there, down to here, along to here, and then down to here. And those dots don't really exist. Just help me draw the thing. Okay. Now, the derivative function for this will be quite different from the one we just finished. Not just in shape, but the way we create it is going to be quite different. When we did this, the first thing that we did so that we could break the shape into regions and deal with each region, 1, 2, 3, 4, is we found the places where the zero tangents are, right? Where the horizontal was. In these guys, it's the corners. And these corners are going to be the way in which we split this shape up. And it's going to be how we're going to be able to draw a sketch because of that. Okay, so I've got a region 1. Between here and here is region 2. Here to here is region 3. From here to here is region 4, and right at the end we have region 5. So there are going to be 5 different regions here. 1, 2, 3, 4, 5. So that's the first difference, right? We use the corners of the shapes as the way to separate it into smaller chunks. Now the next phase, next stage, if you take any point on this line, right, won't the derivative be the same number? So would you agree that if you took a point on this line, in fact, wouldn't the derivative look like the straight line because it would be following right through it? So it's a funny kind of tangent line, but that's what it is. And if it's the same number then, would you also agree it's a positive number? Right, it's pointing upward. So what does that look like in a graph? It means it's a positive number, so it's up here, and it's the same number. So it goes like this. Put a little arrow on that side. Now, region 2, that's a horizontal line. So any point on this piece of the curve is going to have the same derivative, right? The same number. And what number do you get from a horizontal line? You get zeros. And that means from here to here, the curve is a 0. Well, it's not really a curve. The line has a 0 derivative. And let's talk about the boundary, where the corner is. Do you see that on the left-hand side, you have this guy? And on region 2, the right-hand side, you have this guy. Are you happy about a positive derivative and now a 0 derivative? A positive uphill line, a horizontal line. But why are these two open circles? Why do they look like that? Why isn't there a solid dot there or a solid dot there? What's the reasoning?
Because corners are undefined when it comes to slope.
Yeah. There is no single number for the derivative. Good way of phrasing it. Right, now, once you've grasped that, I just keep doing it. It's not really I'm going to change the rules that much. Would you agree that in region 3, it's the same number, but it's negative? In region 4, they're all zeros. The only reason I'm making the 0 ones a little bit thicker is it's hard to tell because the x-axis is in the way, right? And then region 5, would you agree that they're all negative? So that is what the graph of a straight line function looks like. It's a really ugly piecewise function, isn't it? It's broken all over the place. And that's going to happen at every corner. The thing's going to suddenly go from here to here. It's going to be a distinct break in some way, above or below. And the second thing to notice about these shapes aren't they all made up of horizontal lines? Because for each piece of this straight line graph, in any given region, isn't the slope going to be the same number? So a fixed value ends up being horizontal on the derivative. Because at this point, all the derivatives are 10. At this point, all the derivatives are 0. In this region, they're all 0. And here, they're all, whatever it is, -2. Right, that's a little bit different, right? That's a straight line one. Are we cool with that one? And how you tackled it was a little bit different from how we tackled the curves. I got a thumbs up. I like that, so it helps me. Are we good? Anyone else got an issue before I move on?
Why is it piecewise? Like exactly?
Well, piecewise is broken. That's how you would describe a broken. Are you asking why there's a break here? Why is it up here and then down there?
Mm-hmm.
Right. If you look at this side, isn't the derivatives +3? And if you look here, aren't all the derivatives zeros? So +3, imagine that's +3. This would be 3
Right.
and this would be 0. You can't go from 3 to 0 by, well, what some people do, and it's not right, is they just draw a line from here to here because they think things should be like a road, right, joined together. And they're not, they're totally broken, they're piecewise.
Gotcha.
Okay. Good. Now, each situation that I've got in this list, you have to adapt. They're going to be a little bit different. So here is my next one. This is going to be number 3. And we're going to look at what do you do when the function has vertical asymptotes in it. So let's see what I can make happen here. Now, there's no significance to me actually putting these numbers in. They're just kind of a visual help for me. Okay, so let's do a function, a y equals f of x, that has two different kinds of vertical asymptotes in it. And we'll see what we get. And so I'm going to have, I'm going to have a vertical asymptote that looks like this. Right? I'm going to have a vertical asymptote that looks like that. And then I'm going to have a vertical asymptote that looks like that. Would you agree that's a pretty standard looking rational function, right? They kind of look like that. Do you see we got a volcano here? And we got a one of each here, right? So now we're going to have to figure out how can, oops, color change, how we can draw the sketch of the derivative function from only this sketch that's above here. Well, this is a kind of hybrid method. We're going to split this up into regions, just like we did with everything, right? And I'm going to use the vertical asymptotes. So use them as a way of breaking up the region. And I'm going to use that guy there. What do you know about the tangent line there? Zero, yes.
It's 0.
Great. And for no particular reason except maybe cosmetic, this one here, just call it green, and I'm going to put a 0 there. So we now have region 1, region 2, region 3, and finally region 4. Vertical asymptotes end up being probably, in my opinion, the more awkward of the ones we've done so far. Right. Would you agree in region 1 that if I choose any point, that the tangent line is going to be sloping upward, so it's positive? So that means I'm going to be shading positive. Would you agree here the curve is always going to have negative tangent lines? So I'm doing negatives for region 2. There's region 1, there's region 2, region 3, there's 4. In region 3, they're all positives. In region 4, oh, what slope is the tangent line in region 4? If I take any point on this curve, will it be positive or negative?
Positive.
Right. That might look like a mistake. I almost did it myself there. So can you see that we kind of know where the curve is, but there's a lot of unknowns here. See that point there? There is a big temptation for you just to join them. But there is no 0 there. What we have is a vertical asymptote. So if the original function has a vertical asymptote, the derivative is also going to have a vertical asymptote. So let me try and argue why that's the case. As you get closer and closer to this number x equals -3, won't the tangent lines get very, very vertical? And what's the slope of a vertical line? Well, it's either positive infinity or negative infinity, which means it's a vertical asymptote, right? So on this side, won't all the tangent lines be positive and getting more and more and more positive? So that tells me I have a vertical asymptote that goes up the way, right? Gets more and more positive. Now on this side of the curve, as you approach the vertical asymptote, don't the tangent lines get steeper and steeper and steeper? And that means they get big, but negative big, which means that on this side, so what on the original function was a volcano vertical asymptote, hasn't its derivative generated a one of each vertical asymptote? So when you are doing sketches of functions with vertical asymptotes, the derivative is going to have vertical asymptotes, but they may not be the same shape. In fact, they won't be typically. Okay, let's forget about that dot for a minute and focus over here. Same kind of argument. As you get closer and closer, isn't it getting really positive? So it goes up. And what about this side? Well, as you pick points like this one and this one and this one, can you see it getting steeper and steeper and steeper? It's still positive. So guess what? On this vertical asymptote, don't you now end up with a volcano shape?
Question.
Right. Yes.
Why is it still positive if the asymptote is going
This
down?
one?
Yeah.
The asymptote can go down and the function can be positive. So let's try and explain it. See, take that guy there. Would you agree that tangent line is a positive number? It's sloping upwards.
Okay.
Right? And if you take one a bit closer, won't it still be positive? It'll just be steeper, but positive.
Yeah.
And as you get closer and closer, isn't it going to be a bigger and bigger positive number? And that might look intuitively back to front, but we're not talking about the same thing. We're talking about the slope of the curve, not the value of the curve, right? Here it's what's the y coordinate. Here is what's the slope of it, right? So they're not, talking about the same thing. So it's totally okay to have this happen. Right, now, the bit in the middle is going to be easy. Doesn't this guy have to get over to this guy? And isn't there a place for it to do it? So you can see what I would do here is just join them together in some way. Are you comfortable about how these two vertical asymptotes, how you get them to be together? Now, you might think, hey, I'm finished. Well, not quite. Do you notice at the ends here, this function levels off? Happens to level off at the x-axis, but it can level off anywhere. What is going to happen as I start picking values to the left? Won't the slope still be positive, but won't it get less and less and less? And less and less and less, just a fancy way of saying it flatlines at 0. And at this side, it flatlines at 0. So that's how the curve finishes as well. So a vertical asymptote function will generate a derivative function that also has vertical asymptotes at the same places. But would you agree that the shapes are quite different? Volcanoes give you one of each. One of each gives you volcanoes. Happy face gives you, I know what you call that, horizontal point of inflection or something. Right, things change. Are we good with them? Okay. Last kind. The ones I'm calling the rest, which are basically shapes that have non-vertical asymptotes. What on earth am I talking about here? There are two distinct situations that I'm going to deal with. They are very often very simple curves, yet they generate quite weird derivatives. The first is, they're special cases. Let's look at half a circle. Now, right at the top there, there's a horizontal tangent line. So if I drop this guy down to the bottom, would you agree that there's a 0 there? That was pretty straightforward. Would you agree on this side, all the tangent lines are positive? And would you agree on this side, all the tangent lines are negative? And then you might say to yourself, that's it. I can't think of any other information I can get. And so your temptation might be to, I don't know, put a straight line. That's not true, but I can understand why. There is another piece of information that is staring us in the face, but it's hiding really well. If I draw a complete circle, it might help. Right at that point there, isn't the tangent line vertical? Right, as a circle curves round, can you see it's vertical? So see at this point, now I'm calling 3. It's vertical. And at -3, isn't it vertical? Well, how's that going to make things change? Well, I know the derivative is in this region, it passes through the origin and it finishes up in that region, so I'm pretty comfortable I know that. I know it's positive here, right? I know it's negative here, pretty comfortable about that. The finish. Oops. What happens as you get closer to -3? Well, it's positive, and then it's still positive, and then it's still positive. Do you notice something else? Isn't it getting bigger and bigger and bigger? It's getting steeper and steeper and steeper. In fact, won't it eventually be infinite? And doesn't that make vertical asymptotes happen? Right? An infinite derivative means it shoots up. And so it has to shoot upwards. And over here, as you approach x equals 3, right, it's negative, it's sloping downwards, still sloping downwards, but a bit bigger, still sloping downwards a bit bigger. And as you get really close, doesn't it go vertical on you? And vertical, but downwards, right? Because remember where it's coming from, right? It's negatives, means that on this side, it goes down the way, and there we join them. It looks like a kind of, I don't know, kind of like a cubic thing. It's not truly a cubic, it just has a kind of shape to that. Would you agree that's probably the weirdest one of the set? Right. I said there's 2 versions of that. There's lots of versions, but there's 2 I'm going to focus on. So here's a different vertical asymptote situation that was caused by a non-vertical asymptote. I'll even tell you, not that you need to know the function, but I'll give you an example of a function does this. If you sketch the cube root of x, it will look like that. Well, you might say that's no big deal. Well, it does cause problems. And it causes problems in one place. I don't know how well I've done it, but see at the origin? Right there. The tangent line is vertical. Can you trust me? It's vertical, right? Vertical tangent lines mean the derivative is infinity at that point. And if a derivative is infinity at a point, doesn't that make it a vertical asymptote as a derivative, right? You can't get infinite. What you get is vertical asymptotes. So our function, I'll just call it f dash of x now, has a vertical asymptote on the y-axis. On this side, everybody is positive. On this side, everybody, right, meaning all the derivatives are positive. As you get closer, don't the derivatives stay positive, but it gets steeper, which means bigger. So that means on this side, I get a vertical asymptote. And what happens on this side here? Still positive, and as you close in, they get steeper. And there's your guy. So the derivative of a function, say like the cube root of x, has a vertical asymptote in it. Probably not what you would have expected from the cube root, but that's what its derivative looks like. Any questions? Circles cause vertical asymptotes. Some radicals cause vertical asymptotes, even although the original functions are quite nice. Right, there's nothing special about them. Derivatives, not so nice. I'm about to move on if we are good. Okay. This is, I think, going to be a lot easier to do. We're going to do multiple derivatives. And we're going to use the shortcut. Right, there, a nice big ugly polynomial. If I asked you to find its derivative, sometimes called the first derivative, we can do that, can't we? Do it with the shortcut method. So multiply by the power and reduce it by 1. But the good news is, don't we not need to worry about that, make the a and x carry on, right? We can just do it. We x's at the start and still x's when we're finished. So multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. Multiply the power, reduce the power by 1. And what does negative 7x get you? The derivative of negative 7x.
-7.
Right, and what does a plus 3 get you?
Nothing.
Nothing. We comfortable about the shortcut with x's now instead of a's? Now, if you think of that as your starting point, couldn't you differentiate that? Couldn't you find its derivative? And when you do, the notation that we use is f double dashed. You know, the guy who made this notation had no imagination. You agree it's a pretty simple addition to it. And this is sometimes called, for very good reasons, the second derivative. Now, what you do to find the second derivative is just take the first derivative and differentiate it, right? As if it was your starting guy. So multiply by the power, reduce the power by 1, multiply by the power, reduce the power by 1. 10x gets you 10 and the -7 disappears. Now, once you've decided that it's okay to do that, can't you just keep doing it till you feel you don't want to do it anymore? So let's do it, another one. That one is called, not surprisingly, the third derivative. And multiply by the power, reduce it by 1. Now, the notation changes round about here, sometimes a little bit later. You may have noticed that we're using Roman numerals. So you don't do 4 little dashes. The reason you don't do 4 little dashes is, suppose someone went and said that derivative. Can you see it might be quite hard to know if it's 8, 9, or 10, and you could miss one, right? So that's bad notation. So it works well because 1, 2, and 3 kind of follow that. Roman numerals, that's 4. You can also do that notation. Means the same thing. You put a 4 up here and you put brackets around it. And the brackets are so you don't think you're just taking the thing and raising it to the power of 4. That means fourth derivative. Both of them do. In this case, 240. Now, this notation keeps going for a little while and then it dies. And this is what you do for really high powers. For instance, if I said to you, what's that? Not that I can ever imagine any reason in your life you'd want to do it. Wouldn't that be the 103rd derivative? Right, so you started with a function and you differentiated it until you got to 103rd. If I went and said to you, would you be a little bit unsure about what derivative I was talking about if you stuck to Roman numeral notation, right? So can you see why we needed to go in numbers? Now, you might have probably said, well, to heck with it, why don't we just put a bracket around everybody and call the first derivative that guy, you know, and the third derivative that guy? Technically, that is valid, that is correct. But I think the first 2 or 3, which is probably the only ones you realistically ever want to do, isn't that notation kind of pretty and nice and not too ugly? So it kind of survived because of that. But once you get big, you do that. Now, fifth derivative, 0. Have you noticed something about multiple derivatives of polynomials? Every time you take the derivative, doesn't the polynomial reduce by 1? And eventually, won't the polynomial, the derivative become 0? Right. So if you take any polynomial and you keep on finding the derivative and then find the derivative of that and then find the derivative, won't you eventually destroy all the data and it'll just be a 0? Interesting point. You might wonder what on earth is going on there. One day you'll discover what that point is. Are you comfortable with multiple derivatives with polynomials, or do you need to do another one? I think it's pretty much what you probably would have done if nobody told you how to do it, right? Notation's cool. You're comfortable with the brackets or with the Romans, as long as it's not too many. Okay. Then it's perfect timing for the last thing. I'm going to show you a shortcut for the derivatives of simple radicals. So let me show you what I mean by a simple radical. And I'll put beside it what is a complex radical. A simple radical would be cube root of x. 4 times cube root of x. 1/2 fifth root of x. Complex radical. Cube root of x plus 1. 4 times cube root of 2x minus 7. 1/2 fifth root of x squared minus 7x. What makes it simple? What makes it complex? Simple radicals only have x inside the radical, right? So it can only be the cube root of x, 7th root of x, square root of x. The minute there's something else apart from just an x, like an x plus 1 inside it, or a 2x minus 1, or an x squared minus an x, right? The minute you see this, all bets are off. The shortcut method does not work. Don't use the shortcut method. You'll get the wrong answer. You may get an answer, but it'll always be wrong, right? So what I'm about to show you only works for these guys. Does not work for these guys, right? You're not going to be asked any of these in this homework, but later on you might be, and we have to figure out how to do these as a different situation, right? The complex ones. So imagine you are the first person to find the derivative of the cube root of x. And the only rule that you've discovered or someone else told you about it is the power rule. And in English, the power rules goes something like this. Multiply by the power. And reduce the power by 1. And you're thinking to yourself, can I adapt the power rule to this new situation?
Yeah, it's 1/3, right? So multiply it by 1/3.
Okay, so when you say 1/3, I'm assuming
Yeah.
you mean that. We'll take it slow for the others, right? You agree that a cube root can be written as a fractional power? Right. Sorry, I was interrupting, but just so we can get that, continue. It sounds like you're going the right road. What are you going to do
Yeah,
now?
1/3. So then timesing it by 1/3, so it's x/3. And then it's still, is it still 1/2? Just reduced by 1 on the power, or does it get rid of
It is reduced by 1, but think of a third being reduced by 1. In other words, a third take away 1.
It's going to be negative 2/3.
Subtracting 1 from the power, right?
Okay.
So not that 3 is turning into a 2. Don't think that way, but think a third take away 1 from it. Like 5 take away 1 gets you 4, like that kind of way of doing it. Now, if you take 1 away from that, won't you end up with a rather awkward negative 2/3? Agreed? Now, this might be a good point for me to introduce a new piece of notation. When we do y equals f of x, we very often use that, right? Right, that's the notation. There is another notation that I'm now going to introduce, and it's that guy. And it's you read it out loud as dy by dx. It's just another notation that means the derivative. Why do we kind of need that notation? Because if I want to label this as a derivative, I don't have an f of x to work with. Don't I just have a y equals to work with? So if I want to tell people I've now got the derivative, the notation that I'm going to use is probably this. Right. So if you get a question that says f of x equals x cubed, then you will probably write down the derivative f dashed of x is 3x squared. But if somebody says y equals x cubed, you're going to say the derivative, dy by dx, is 3x squared. Can you see that it's just, the notation is to fit the way the question is phrased. Some questions are called y equals x cubed, right? And some questions are called f of x equals x cubed. And when you have that, it's helpful if you have another notation to indicate that. Now, that's the answer, right? You multiply by the power and you reduce it by 1. But we have style point rules. What do I mean by style point rules? You want it to make it look pretty. And pretty involves things like factor the heck out of it, collect like terms, and lastly, make it look like the original. Now, do you see how the original is a cube root? A radical. Isn't this a fractional power? And it's negative. So the next piece of the puzzle is that this can be written down as that. Are we happy about a negative power becoming a positive power on the bottom? That's an algebraic thing, right? This guy is downstairs. Notice the 3's there. Now, I don't know, well, I do know when you did this because I'm actually teaching it right now, or I will be in a few days. Aren't fractional powers radicals? And can't you go from radicals to fractional powers, which is this way. But can't you go from fractional powers and rewrite them back as radicals? And I want this guy to look like him. So x to the 2/3 is the cube root of x squared. And that is the style point answer. That's the kind of way I would expect it to be written. So it's not that we're doing calculus. Aren't we just doing some algebra on how to rearrange things to be written in a different form so that it more closely matches the top? In these questions, you are not going to have collect like terms happening, although that will happen in the future. And in these questions, you're not going to be doing any factoring the heck out of it either, right? But what you probably are going to be doing in these questions is making it look like the original. Try another one. Oops. Suppose I had 4 square root of x's. And the first thing you do is write it as a fractional power. Like Robin was saying, you can then multiply by the power. Okay, if you multiply this by a half, are you okay with where the 2's coming from, right? 4 times a half gets me 2. Now, when you reduce the power by 1, you take this power, right, it's a half. If you take 1 away from it, would you agree you get negative a half? A half, reduce it by 1, negative a half, right? Okay, style points. I want to make this look pretty. What do I do first in this question?
Move the x to the denominator instead of the numerator.
And then to finish, what do we do to complete the package?
Write it back as a square root. So square root of x.
Right. Now, I don't know if I'm convincing you, but even if I don't convince you, will you still do it? That this is considered better form. Now, if you look at it, can you see that it does kind of look like the original? It's got the same shape. And in many ways, isn't this a better way to think of the function? When I see this, I can see it better. I can get an idea of what its values are. If somebody said to you, 4x to the negative 3/4, wouldn't you be puzzled about, I'm not quite sure what that looks like or what its values are or when it might have problems? If I write it like this, do you see you're going to have a problem at 0? If I write it like this, can you see that you're never going to be able to use negative numbers? If I leave it like that, you might not be able to see those things, or at least not as easily. Right. Okay, last one for today is a good way to finish. 6 cube root of x to the 7. That's just going crazy. That's going to be x to the 7/3. We've done that before, right? 7/3. Derivative. Multiply by the power, that gets you 14. Reduce the power by 1. What do you get as your new power if you take 1 away from the whole number 1, away from 7/3?
One-third.
4/3.
4/3. 4/3.
Agreed.
Yes.
4/3. Now, have you noticed in this case, I don't have the negative issue, right? There is no negative powers to worry about, but I still have to make it look pretty. In this case, cube root, because the bottom is 3 of x to the 4. Finito. Finished. Hey, isn't it nice that the shortcut method, the power rule, works for radicals, or at least simple radicals?
Could we not
Doesn't
use
that mean
multiple derivatives and make it
Yeah.
1/3 and then negative 2/3?
Yeah, and keep going till you get bored. So you can do derivatives and multiple derivatives using the rule. Yeah, nothing wrong with that. I mean, they'll get messy and ugly probably and weird. You know, won't always get whole numbers here, right? We'll start getting 14 thirds and it's really messy, but it'll be doable. Right. Say hi and bye-bye.